Tonight on The Sleepy Scientist, we're drifting gently through the vast cosmic ocean, toward one of the most extraordinary objects in our universe. In the quiet space of our imagination, we'll explore what would happen if we found ourselves falling into WO102, the hottest star known to humanity. Gently, we discover that this isn't a journey of fear or destruction, but rather a contemplative exploration of stellar physics, nuclear processes, and the profound beauty that exists in the most extreme environments our universe can create. Like whispers in the night, the laws of physics will guide us through this theoretical voyage, teaching us about temperature, radiation, plasma dynamics, and the very processes that forge the elements of which we are made. WO102, also known as WO10, resides approximately 26,000 light-years away from Earth. Nestled within the constellation Sagittarius, this Wolf-Rayet star burns at a surface temperature of roughly 210,000 Kelvin, nearly 40 times hotter than our gentle Sun. To put this in perspective, our Sun's surface temperature is about 5,800 Kelvin, warm enough to sustain life on our peaceful planet. But WO102 exists in a realm of such intense heat that it challenges our understanding of stellar physics. As our journey continues into this exploration, we must first understand what makes a Wolf-Rayet star so unique. These are massive stars, typically between 10 to 25 times the mass of our Sun, that have evolved beyond their main sequence phase. They've shed their outer hydrogen layers through powerful stellar winds, revealing their hot, helium-rich cores to the cosmos. The name comes from French astronomers Charles Wolf and Georges Rayet, who first identified this class of stars in 1867 through spectroscopic observations that revealed unusual emission lines. In the quiet space of stellar evolution, Wolf-Rayet stars represent a brief but spectacular phase in the life of the most massive stars. They burn through their nuclear fuel at an extraordinary rate, living fast and bright before ultimately exploding as supernovae or collapsing into black holes. WO102 is particularly special because it holds the record for the highest surface temperature ever measured in a star, a cosmic furnace that burns with the intensity of 210,000 degrees Kelvin. Let's drift into a deeper understanding of what this temperature truly means. At such extreme heat, matter exists in a state completely alien to our everyday experience. Atoms are stripped of their electrons, creating a plasma so energetic that the very concept of solid, liquid, or gas becomes meaningless. The radiation pressure from this incredible heat is so intense that it drives stellar winds at velocities exceeding 5,000 kilometers per second. That's nearly 2% the speed of light. Now we float toward comprehending the scale of this stellar giant. While WO102's exact size is difficult to measure due to its extreme brightness and the obscuring effects of its stellar winds, estimates suggest it has a radius roughly 0.9 times that of our Sun. This might seem small for such a massive star, but remember, this star has shed its outer layers, revealing its incredibly dense hot core. It's like peeling away the cool outer layers of an onion to reveal the intense center within. Gently, we discover that the light from WO102 is so intense that it outshines our Sun by a factor of nearly 300,000. If we could somehow replace our Sun with WO102, Earth would be instantly vaporized, not by the star's heat, but by the sheer intensity of its radiation. The energy output is so tremendous that it ionizes gas clouds across hundreds of light-years of space, creating beautiful nebulae that glow with the borrowed light of this stellar furnace. In the quiet space of our contemplation, we begin to appreciate that falling into such a star would be unlike anything we could experience elsewhere in the universe. It would be a journey through states of matter and energy that exist nowhere else. A voyage through temperatures and pressures that challenge the very foundations of physics as we understand them. Like whispers in the night, the story of WO102 tells us about the life cycles of the most massive stars, about nuclear fusion, about the creation of heavy elements, and about the ultimate fate of stellar objects that burn too bright and too fast to sustain themselves for billions of years like our gentle Sun. As our journey continues, we'll explore each phase of this theoretical fall. From the moment we begin approaching this stellar giant across the vast emptiness of space, Through our encounter with its powerful stellar winds and ultimately to our transformation within the nuclear furnace at its heart, we'll discover how the extreme physics of this environment would affect matter, energy, and time itself. Let's drift into this cosmic meditation with open minds and peaceful hearts, ready to learn about one of the universe's most extreme environments, while maintaining the gentle contemplative approach that helps us find wonder in the cosmos without fear or anxiety. Tonight, we become temporary stardust, joining the eternal dance of matter and energy that has been playing out across the universe for billions of years. Now we float toward beginning our journey, but first, let us take a moment to appreciate the scientific instruments and observations that have allowed us to study WR102 from our safe distance here on Earth. The Hubble Space Telescope, the Spitzer Space Telescope, and ground-based observatories around the world have combined their observations to reveal the secrets of this extraordinary star. Gently, we discover that studying Wolf-Rayet stars like WR102 is crucial for understanding stellar evolution, supernova explosions, and the chemical enrichment of the universe. These stars are cosmic alchemists, fusing lighter elements into heavier ones through nuclear processes, then dispersing these newly created elements into space through their powerful stellar winds and eventual explosive deaths. In the quiet space of scientific observation, astronomers have learned that WR102 is losing mass at an incredible rate, roughly 1 solar mass every 100,000 years. This might seem like a long time, but for a star, it's equivalent to rapid weight loss. The stellar winds carrying away this mass are moving at such high velocities that they create shock waves when they collide with the surrounding interstellar medium. Like whispers in the night, the spectroscopic signature of WR102 tells the story of its composition and physical conditions. The strong emission lines in its spectrum reveal the presence of highly ionized helium, carbon, and oxygen, elements that speak to the nuclear processes occurring within the star's core and the extreme temperatures at its surface. As our journey continues into this theoretical exploration, we carry with us the knowledge that has been painstakingly gathered by generations of astronomers. Each observation, each spectrum, each measurement has contributed to our understanding of these extreme stellar objects. We approach WR102 not as naive explorers, but as informed cosmic travelers, armed with the scientific knowledge that will help us understand what we encounter along the way. Let's drift into the first phase of our journey now, as we begin our approach to this stellar giant from the cold, empty depths of interstellar space. The voyage ahead will take us through environments that exist nowhere else in the universe, through temperatures and pressures that would seem impossible if we didn't have the theoretical framework of stellar physics to guide our understanding. Now we float toward WR102, beginning a journey that will transform our perspective on stellar physics, nuclear processes, and the fundamental nature of matter and energy in the most extreme environments the universe can create. In the quiet space of our cosmic journey, we must first fully comprehend the nature of the stellar giant we're approaching. WR102 belongs to a special class of stars known as Wolf-Rayet stars, named after the French astronomers Charles Wolf and Georges Rayet, who first identified these unusual stellar objects in 1867. These astronomers were conducting spectroscopic observations at the Paris Observatory when they noticed stars with peculiar emission lines that didn't match the absorption lines typically seen in stellar spectra. Gently, we discover that Wolf-Rayet stars represent one of the most extreme phases in stellar evolution. They are the exposed cores of originally very massive stars, typically those born with 20 to 50 times the mass of our Sun. Through powerful stellar winds and mass loss, these giants have stripped away their outer hydrogen-rich layers, revealing their hot, helium-burning cores to the cosmos. It is as if the universe has peeled back the cooler outer layers of these stars to reveal the blazing nuclear furnace within. Like whispers in the night, the classification system for Wolf-Rayet stars tells us about their composition and evolutionary stage. WR102 belongs to the WO class, the oxygen-rich Wolf-Rayet stars that represent the final phase of Wolf-Rayet evolution. These are stars that have progressed through burning hydrogen, then helium, and are now fusing carbon and oxygen in their cores. The Ca designation in W10 indicates that this star was initially catalogued as a potential luminous blue variable before being reclassified as a Wolf-Rayet star. As our journey continues deeper into understanding this stellar phenomenon, we encounter the remarkable fact that Wolf-Rayet stars are relatively rare. In our Milky Way galaxy, which contains hundreds of billions of stars, fewer than 300 Wolf-Rayet stars have been identified. This rarity stems from the brief nature of the Wolf-Rayet phase. These stars burn through their nuclear fuel so rapidly that they exist in this state for only a few 100,000 years, a mere blink of an eye in cosmic terms. Let's drift into comprehending the extraordinary mass loss that characterizes these stellar giants. W102 is losing approximately 1 solar mass, that is the entire mass of our Sun, every 100,000 years through its stellar winds. These winds race away from the star at velocities exceeding 5,000 kilometers per second, carrying with them the products of nuclear fusion that have been created in the star's core. This mass loss is so intense that it creates an expanding bubble of hot gas around the star, often forming beautiful nebulae that we can observe with our telescopes. Now we float toward understanding the nuclear processes that power W102's incredible luminosity. In the core of this stellar giant, temperatures reach over 100 million Kelvin, conditions so extreme that carbon and oxygen nuclei can overcome their mutual electrical repulsion and fuse together. This process, known as carbon burning and oxygen burning, releases enormous amounts of energy while simultaneously creating heavier elements like neon, magnesium, silicon, and sulfur. In the quiet space of stellar nuclear synthesis, W102 is actively creating the heavy elements that are essential for planet formation and life as we know it. The carbon in our bodies, the oxygen we breathe, the silicon in computer chips, the iron in our blood, all of these elements were forged in the nuclear furnaces of massive stars, like W102. When this star eventually explodes as a supernova, it will scatter these newly created elements across space, seeding future generations of stars and planets. Gently, we discover that the surface temperature of W102, approximately to 110, 0 Kelvin, is hot enough to ionize virtually any atom. At such extreme temperatures, electrons are stripped away from atomic nuclei, creating a plasma state where matter behaves according to the laws of magnetohydrodynamics. Rather than ordinary thermodynamics, the radiation from this superheated surface is so intense that it peaks in the extreme ultraviolet and soft X-ray portions of the electromagnetic spectrum. Like whispers in the night, the photons streaming from WR100 to S surface carry enough energy to ionize hydrogen atoms across hundreds of light-years of space. This creates vast H2 regions, clouds of ionized hydrogen gas that glow with characteristic pink and red colors as electrons recombine with protons and emit light. These nebulae serve as cosmic beacons, marking the locations of the most massive stars in our galaxy. As our journey continues, we must appreciate the role that radiation pressure plays in shaping W102's structure and behavior. The intense radiation generated by nuclear fusion in the star's core creates an outward pressure that helps support the star against gravitational collapse. However, this radiation pressure is so strong that it also drives the powerful stellar winds that strip away the star's outer layers. It's a delicate balance between the inward pull of gravity and the outward push of radiation. Let's drift into understanding the magnetic fields that thread through W102's atmosphere and stellar winds. While direct observations of magnetic fields in Wolf-Rayet stars are challenging due to their extreme brightness and rapid rotation, theoretical models suggest that these stars possess complex magnetic field structures. These fields can channel and accelerate the stellar winds, creating spiral patterns and shock waves as the magnetized plasma interacts with the surrounding interstellar medium. Now we float toward comprehending the rotation of WR102. Many Wolf-Rayet stars are rapid rotators, spinning at velocities approaching their breakup speed, the point at which centrifugal forces would overcome gravity and tear the star apart. This rapid rotation affects the star's shape, making it oblate rather than perfectly spherical. and influences the pattern of mass loss through stellar winds, the interaction between rotation, magnetic fields, and radiation pressure creates a complex three-dimensional structure in the star's atmosphere. In the quiet space of our contemplation, we consider the companion stars that often orbit around Wolf-Rayet stars. Many WR stars exist in binary systems, with companion stars that can be affected by the intense radiation and stellar winds of the Wolf-Rayet primary. In some cases, material from the companion star can be stripped away and accreted onto the Wolf-Rayet star, affecting its evolution and ultimate fate. While WR102's binary status is still being studied, the presence of a companion would add another layer of complexity to our theoretical journey. Gently, we discover that the spectroscopic observations of WR102 reveal a wealth of information about its physical conditions. The strong emission lines of highly ionized helium, carbon, and oxygen tell us about the temperature and density structure of the star's atmosphere. The Doppler broadening of these lines indicates the turbulent velocities within the stellar winds, while their relative intensities provide clues about the abundance of different elements. Like whispers in the night, the infrared observations of WR102 reveal the presence of dust grains forming in the cooler regions of its stellar wind. Despite the extreme temperatures close to the star, as the stellar wind expands and cools, conditions become favorable for the condensation of refractory materials like carbon dust. These tiny grains absorb the star's intense ultraviolet radiation and re-emit it as infrared light, creating a thermal signature that we can detect with space-based infrared telescopes. As our journey continues, we must understand the evolutionary pathway that led to WR102's current state. This star began its life as an extremely massive main sequence star, fusing hydrogen into helium in its core for several million years. As the hydrogen fuel in the core was exhausted, the star expanded into a red supergiant phase, with a cool, extended atmosphere. Powerful stellar winds and possibly interactions with a companion star then stripped away the hydrogen-rich envelope, revealing the hot helium-burning core that we see today. Let us drift into appreciating the brief but spectacular future that awaits WR102. Current models suggest that this star will continue burning heavier elements in its core, carbon, oxygen, neon, magnesium, silicon, in a series of nuclear burning phases that occur on increasingly shorter time scales. Eventually, the core will attempt to fuse iron, but iron fusion absorbs energy rather than releasing it, leading to a catastrophic collapse and a spectacular supernova explosion. Now we float toward understanding the supernova that will mark the end of WR102's life. As a very massive star, WR102 is destined to explode as either a Type Ib or Type Ic supernova events characterized by the absence of hydrogen lines in their spectra, reflecting the fact that these stars have already lost their hydrogen-rich outer layers. The explosion will be so bright that it could potentially outshine the entire Milky Way galaxy for several weeks, dispersing the heavy elements created during the star's lifetime across hundreds of light years of space. In the quiet space of cosmic recycling, we appreciate that the death of WR102 will contribute to the chemical evolution of our galaxy. The shock waves from its supernova explosion will compress nearby gas clouds, potentially triggering the formation of new stars. Some of these new stars will form planetary systems, and the heavy elements dispersed by WR102's death may eventually become incorporated into rocky planets like Earth. Gently, we discover that WR102 may also leave behind a compact remnant after its supernova explosion. Given its high mass, the collapsing core may form either a neutron star or a black hole. If a black hole forms, it could have a mass of 10 to 20 times that of our Sun, joining the population of stellar mass black holes that dot our galaxy. These remnants serve as cosmic laboratories for studying extreme physics, from the behavior of matter at nuclear densities to the effects of strong gravitational fields on space and time. Like whispers in the night, the study of Wolf-Rayet stars like WR102 has revealed important insights about stellar evolution, supernova explosions, and the chemical enrichment of the universe. These observations have helped astronomers understand how the most massive stars live and die, how heavy elements are created and dispersed, and how stellar explosions can trigger the formation of new generations of stars and planets. As our journey continues toward our theoretical encounter with WR102, we carry with us this deep understanding of stellar physics, nuclear processes, and cosmic evolution. We approach this star not as a hostile environment to be feared, but as a natural laboratory where the fundamental laws of physics play out on the grandest scales. The extreme conditions we'll encounter, temperatures, pressures, and radiation fields beyond anything found elsewhere in the universe, represent the ultimate expression of stellar physics. Let's drift into the next phase of our journey now, as we begin our approach to WR102 across the vast emptiness of interstellar space. Armed with our scientific understanding, we can appreciate each phenomenon we encounter as a manifestation of the physical laws that govern the behavior of matter and energy under extreme conditions. Now we float toward WR102, ready to begin our theoretical voyage through one of the most extreme environments the universe has to offer. In the quiet space of our cosmic journey, we begin our approach to WR102 from the cold emptiness of interstellar space. Imagine ourselves starting this voyage from a distance of approximately 1 light-year away, a vantage point where the star appears as merely the brightest point of light in a field of distant suns. At this distance, we're still within the realm of ordinary interstellar space, where the temperature hovers around 2.7 Kelvin, the cosmic microwave background radiation left over from the Big Bang. Gently, we discover that even at this vast distance, WR102's influence on its surroundings is already apparent. The star's intense radiation has cleared a cavity in the interstellar medium, creating what astronomers call a stellar wind bubble or Wolf-Rayet bubble. This cavity, carved out by millions of years of powerful stellar winds, extends for several light-years in all directions, creating a relatively empty region of space around the star. Like whispers in the night, the interstellar medium through which we travel tells the story of previous generations of stars. The gas and dust between the stars contains elements heavier than hydrogen and helium-carbon, oxygen, silicon, iron, that were forged in the nuclear cores of ancient stars and dispersed through supernova explosions. As we drift toward WR102, we're traveling through this enriched material, the recycled stellar debris that will one day form new stars and planets. As our journey continues inward, reducing our distance to perhaps half a light-year, we begin to notice the first subtle effects of WR102's stellar wind. The density of interstellar gas around us starts to decrease as we enter the rarefied cavity, carved out by the star's powerful outflows. The temperature of the surrounding medium begins to rise slightly as we encounter gas that has been heated by shock waves from the stellar wind interacting with the interstellar medium. Let's drift into understanding the nature of the stellar wind we're beginning to encounter. Unlike the gentle solar wind from our Sun, which carries away about 1/1,000,000th of a solar mass per year, WR102's stellar wind is removing approximately 1 solar mass every 100,000 years, a mass loss rate that is 10,000 times greater than our Sun's. This wind consists primarily of helium, carbon, and oxygen ions accelerated to velocities exceeding 5,000 kilometers per second by the intense radiation pressure from the star's surface. Now we float toward a distance of 0.1 light-years, roughly 6,000 times the distance from Earth to the Sun. At this range, WR102 has grown from a point of light to a visible disk, blazing with an intensity that would be painful to observe directly. The star's luminosity is approximately 300,000 times greater than our Sun's, making it one of the most luminous objects in our galaxy. The blue-white light streaming toward us carries enough energy to begin ionizing any hydrogen atoms in our vicinity. In the quiet space of our approach, we begin to feel the effects of WR102's intense radiation field. Gently, we discover that the magnetic field embedded in WR102's stellar wind is beginning to affect our surroundings. As the magnetized plasma streams past us at thousands of kilometers per second, it creates a complex structure of magnetic field lines that spiral outward from the star. These fields can trap and accelerate charged particles, creating cosmic rays that race through the stellar wind at nearly the speed of light. Like whispers in the night, the density fluctuations in the stellar wind create beautiful structures visible in the light, scattered by dust grains. Even though the wind is highly supersonic, it has not perfectly smooth. Instabilities and turbulence create clumps and streamers of denser material that shine by reflected starlight. These structures evolve and change as they flow outward, creating a dynamic, ever-changing environment around the massive star. As our journey continues to a distance of 0.01 light-years, about 600 times the Earth-Sun distance, the effects of WR100 to S extreme environment become increasingly dramatic. The stellar wind density around us has increased significantly, and we're now immersed in a flow of plasma moving at several thousand kilometers per second. The temperature of this wind material has risen to over 40,000 Kelvin due to heating by the star's intense radiation. Let's drift into appreciating the scale of the forces at work around us. The radiation pressure from WR100's photons is now strong enough to overcome the gravitational attraction of small particles, effectively blowing away any dust grains or small objects in our vicinity. This radiation pressure is what drives the stellar wind in the first place. The intense photon flux from the star's surface transfers momentum to the atoms in the stellar atmosphere, accelerating them to escape velocity and beyond. Now we float toward a distance of 1,000 times the Earth-Sun distance, where WR100 dominates our sky with its brilliant blue-white radiance. The star appears roughly the same angular size as our Sun does from Earth, but its surface brightness is almost unimaginably intense. The energy flux reaching us is now thousands of times greater than the solar constant at Earth, hot enough to vaporize virtually any solid material. In the quiet space of this closer approach, we witness the birth of the stellar wind through direct observation. The star's atmosphere extends well beyond its visible surface, forming a complex structure of shock waves, compression zones, and rarefied regions where the transition from bound atmosphere to freely flowing wind takes place. The physics governing this transition from a gravitationally bound stellar atmosphere to a supersonic outflow represents one of the most complex problems in stellar astrophysics. Gently, we discover that the stellar wind is not uniform in all directions. Observations of many Wolf-Rayet stars reveal that their winds can be aspherical, with faster, denser flows along certain directions and slower, more rarefied flows in others. This asymmetry may be caused by the star's rotation, magnetic fields, or the presence of a binary companion. As we approach WR102, we might find ourselves in a particularly dense wind stream or in a relatively quiet region. Between such streams, like whispers in the night, the spectroscopic signature of the stellar wind tells us about the physical conditions. In this extreme environment, the emission lines from highly ionized atoms, helium with both electrons stripped away, carbon with 4 or 5 electrons missing, oxygen with 6 electrons removed, reveal the incredible temperatures and ionization conditions present in the wind. The Doppler shifts and line profiles tell us about the velocity structure and turbulence within the outflow. As our journey continues inward to a distance of 100 times the Earth-Sun distance, we enter what might be called the interstellar wind region. Here, the wind is still accelerating, gaining speed as it flows away from the star under the relentless pressure of WR102's radiation. The plasma around us is so hot and ionized that it exists in a state, unlike anything found naturally on Earth, a fully ionized gas where atomic nuclei and electrons move independently at velocities determined by the local temperature and magnetic field structure. Let's drift into understanding the heating mechanisms at work in this environment. While the stellar wind starts hot due to the extreme surface temperature of WR102, it experiences additional heating as it flows outward. Shock waves within the wind, caused by instabilities and variations in the mass loss rate, can heat the plasma to even higher temperatures. Magnetic reconnection events, where magnetic field lines break and reconnect, can also deposit energy into the wind material. Now we float toward a distance of 10 times the Earth-Sun distance, where the environment becomes increasingly hostile to ordinary matter. The stellar wind velocity has reached several thousand kilometers per second, and the plasma temperature exceeds 100,000 Kelvin. At these conditions, even the most refractory materials would be vaporized and ionized. Any atoms in our vicinity exist as bare nuclei surrounded by a sea of free electrons. In the quiet space of this extreme environment, we begin to appreciate the role of radiative processes in shaping our experience. The intense radiation field from WR102 is constantly interacting with the wind material, exciting atoms to higher energy states, and then allowing them to decay back down, emitting photons in the process. This creates a rich emission spectrum that astronomers use to diagnose the physical conditions in Wolf-Rayet stellar winds. Gently, we discover that time dilation effects, while still negligible at our current speeds, begin to become theoretically interesting as we're accelerated by the stellar wind and radiation pressure. Although we're nowhere near relativistic velocities, the extreme gravitational field of this massive star and our motion through it would cause tiny, but measurable effects on the passage of time compared to a distant observer. Like whispers in the night, the magnetic field structure around us becomes increasingly complex as we approach the star. The stellar magnetic field, while probably much weaker than the magnetic fields of less massive stars due to the convective nature of WR100's atmosphere, still plays a role in shaping the wind structure. Magnetic field lines can become twisted and distorted by the outflowing plasma, creating a complex topology that influences how charged particles move through the wind. As our journey continues to a distance of just a few times the Earth-Sun distance, we approach the region where the stellar wind transitions from its acceleration phase to its constant velocity cruise phase. This is also the region where dust grains, if any exist, would be rapidly destroyed by the intense radiation and collisions with high-velocity wind particles. The environment has become so extreme that only the most basic particles, protons, alpha particles, electrons, and the nuclei of heavier elements can survive. Let's drift into contemplating the view of WR102 from this close distance. The star now fills a significant portion of our sky, blazing with a surface brightness that would instantly blind any conventional optical instrument. The stellar surface shows a complex structure of hot spots, convective cells, and regions of varying temperature and density. The boundary between the star's surface and its atmosphere becomes increasingly difficult to define as we witness the transition from bound stellar material to freely flowing wind. Now we float toward the final phase of our approach. As we near a distance comparable to the star's radius, roughly the distance from the Sun's center, to its surface, at this proximity, we're no longer external observers of WR102's stellar wind, but participants in the complex plasma physics that governs the star's outer atmosphere. The distinction between the stellar surface and the wind becomes academic as we encounter material that is in the process of escaping from the star's gravitational well. In the quiet space of this closest approach, we prepare for the transition from observer to participant in the extreme physics of WR102's environment. The next phase of our journey will take us from the realm of stellar winds and radiation pressure into the even more extreme conditions within the star's atmosphere, and eventually its nuclear burning core. Gently, we discover that our theoretical journey has already taken us through conditions more extreme than anything found in our solar system. The temperatures, densities, velocities, and radiation fields we've encountered during our approach to WR102 exceed those found even in the most energetic phenomena near Earth. Yet this has been merely the prelude to our exploration, the gentle introduction to the cosmic furnace that awaits us within the star itself. Like whispers in the night, the physics we've witnessed during our approach, radiation pressure, plasma dynamics, stellar winds, and magnetic field interactions represent fundamental processes that occur throughout the universe, wherever matter and energy interact under extreme conditions. Our journey to WR102 has been an exploration not just of one unusual star, but of the physical laws that govern the behavior of matter and energy in the cosmos. As our journey continues, we prepare to cross the threshold from interplanetary to stellar environments, from the relatively familiar physics of hot gases and radiation to the exotic realm of stellar atmospheres and nuclear fusion. The next phase of our voyage will take us into conditions where the very nature of matter and energy becomes transformed by temperature and pressure beyond our everyday experience. Now we float toward the stellar atmosphere of WR102, ready to begin our descent into one of the most extreme environments the universe has to offer. In the quiet space of our cosmic meditation, we now cross the threshold from the stellar wind environment into the outer atmosphere of WR102 itself. This boundary is not sharp like the surface of a solid planet, but rather a gradual transition where the density of stellar material begins to increase, and the physics becomes dominated by the star's gravitational field, rather than the outward flow of its wind. Gently, we discover ourselves entering what stellar physicists call the photosphere, the layer of the star, from which most of the visible light is emitted. For WR102, this photosphere exists at a temperature of approximately 210,000 Kelvin, nearly 40 times hotter than the surface of our Sun. At this temperature, the Stefan Boltzmann law tells us that each square meter of the stellar surface is radiating over to 0.5 billion times more energy than the same area on our Sun's surface. Like whispers in the night, the photons streaming past us carry the signatures of the extreme physics. At work in this environment, most of the radiation is in the far ultraviolet and soft X-ray regions of the electromagnetic spectrum. Photons with energies tens to hundreds of times greater than visible light. These high-energy photons are capable of ionizing any atom they encounter, stripping away electrons and leaving behind bare atomic nuclei. As our journey continues deeper into the stellar atmosphere, we encounter densities that begin to approach those found in the outer layers of normal stars. However, the composition is radically different from what we might expect. Instead of the hydrogen-rich material that makes up most stellar atmospheres, WR102's atmosphere consists primarily of helium, with significant amounts of carbon and oxygen, the products of nuclear fusion, that have been dredged up from the star's interior through convective mixing and mass loss. Let's drift into understanding the hydrostatic equilibrium that governs the structure of WR102's atmosphere. Even in this extreme environment, the fundamental balance between gravitational pressure trying to compress the star and radiation pressure trying to expand it still applies. However, the radiation pressure is so intense that it nearly equals the gravitational pressure, making the star's structure delicately balanced and prone to instabilities. Now we float toward the temperature minimum region, a layer in the stellar atmosphere where the temperature briefly decreases with depth, before rising again toward the stellar interior. In normal stars like our Sun, this temperature minimum occurs at relatively cool temperatures of a few thousand Kelvin, but in WR102, even the coolest part of the atmosphere maintains temperatures exceeding 100,000 Kelvin, hot enough to ionize virtually any element. In the quiet space of stellar spectroscopy, the light around us tells the story of atomic physics under extreme conditions. The emission lines we observe are broadened not just by thermal motion, atoms moving at tens of kilometers per second due to their high kinetic energy, but also by the Stark effect, where the intense electric fields from nearby ions split spectral lines into multiple components. The result is a complex spectrum that requires sophisticated theoretical models to interpret. Gently, we discover that the convective processes in WR102's atmosphere create a dynamic, turbulent environment unlike the relatively stable atmospheres of cooler stars. Hot bubbles of plasma rise from the interior while cooler though still incredibly hot material sinks back down, creating a roiling, chaotic motion that mixes the stellar material and transports energy from the interior to the surface. Like whispers in the night, the magnetic fields threading through the stellar atmosphere create additional complexity. In this already extreme environment, while WR102's magnetic field is probably weaker than that of our Sun, due to the star's fully convective structure, it still plays a role in channeling the flow of plasma and creating localized heating through magnetic reconnection events. As our journey continues deeper into the star, we begin to encounter the effects of degeneracy pressure, a quantum mechanical effect that becomes important at the high densities found in stellar interiors. As we compress matter to higher and higher densities, the electrons are forced into higher energy states according to the Pauli exclusion principle, creating an additional pressure component that helps support the star against gravitational collapse. Let's drift into the realm of radiative transfer, where photons created by nuclear fusion in the star's core begin their million-year journey to the surface. In the dense interior of WR102, photons can travel only a few centimeters before being absorbed and re-emitted by an atom or ion. This creates a random warp process where energy slowly diffuses outward from the core, through countless absorption and emission events. Now we float toward the convective zone that extends from WR102's core nearly to its surface. Unlike our Sun, which has a radiative interior and convective outer layer, WR102 is convective throughout most of its structure. This means that hot plasma is constantly rising from the deep interior, while cooler material sinks back down, creating an efficient mixing mechanism that brings the products of nuclear fusion to the surface. In the quiet space of stellar evolution, we appreciate that this convective mixing is what gives Wolf-Rayet stars their characteristic spectroscopic signatures. The carbon, oxygen, and other heavy elements we observe in WR100's spectrum were created by nuclear fusion in the star S core and brought to the surface by convective motions. This mixing process also helps drive the powerful stellar winds that strip away the star's outer layers. Gently, we discover that the equation of state governing the behavior of matter in WR102's interior is far more complex than the ideal gas law that describes ordinary gases. At the extreme temperatures and densities we're encountering, we must account for radiation pressure, electron degeneracy, ion-ion interactions, and relativistic effects. The plasma behaves more like a relativistic fluid than a simple gas. Like whispers in the night, the nuclear reactions occurring around us begin to influence our local environment. Even though we race still in the stellar atmosphere rather than the core, the intense flux of high-energy photons and particles from nuclear fusion creates a background of gamma rays and neutrinos that permeate the entire stellar structure. While neutrinos pass through us without interacting, the gamma rays deposit their energy in the stellar material, contributing to the heating and ionization of our surroundings. As our journey continues inward, we encounter the first effects of time dilation due to the strong gravitational field of this massive star. While still relatively small compared to the extreme time dilation near a black hole, the effects are measurable. Time passes slightly more slowly for us deep in WR100's gravitational well, compared to an observer at a great distance from the star. Let's drift into understanding the role of opacity in determining the stellar structure around us. Opacity, the measure of how easily photons can travel through stellar material, depends on temperature, density, and composition. In WR102's interior, the high temperatures ionize atoms completely, reducing the opacity and allowing photons to travel more freely than they would in cooler stellar material. Now we float toward the region where electron scattering becomes the dominant source of opacity. At the extreme temperatures in WR102's interior, most atoms are completely ionized, leaving free electrons that can scatter photons through Thomson scattering. This process doesn't change the photon's energy, but does change its direction, contributing to the random walk that photons must take to escape from the stellar interior. In the quiet space of quantum mechanics, we begin to encounter phenomena that don't exist under normal conditions. The high temperatures and densities create conditions where quantum effects become important. For understanding the behavior of matter, electron degeneracy pressure, the Pauli exclusion principle, and quantum statistical mechanics all play roles in determining the physical properties of our environment. Gently, we discover that the chemical composition around us is constantly evolving due to nuclear reactions, while the overall structure of the star changes slowly. The local abundance of different isotopes and elements is continuously modified by nuclear fusion, radioactive decay, and neutron capture processes. We're witnessing the ongoing process of stellar nuclear synthesis, the creation of heavy elements from lighter ones. Like whispers in the night, the pulsations and oscillations of WR100 to create variations in temperature, density, and pressure around us. Many Wolf-Rayet stars show evidence of variability. possibly due to strange mode instabilities or other oscillation mechanisms. These pulsations can compress and rarefy the stellar material, creating waves that propagate through the star's interior. As our journey continues toward the nuclear-burning regions of WR102, we prepare to encounter conditions that exist nowhere else in the universe, except in the cores of the most massive stars. The temperatures and densities we'll soon experience are sufficient to fuse carbon and oxygen into even heavier elements, continuing the process of stellar nuclear synthesis that creates the periodic table of elements. Let us drift into contemplating the remarkable fact that the extreme conditions we're experiencing in WR102's interior represent the culmination of billions of years of stellar evolution. This star began its life as a massive main sequence star, gradually evolving through different nuclear burning phases until it reached its current state as an exposed helium-burning core surrounded by powerful stellar winds. Now we float toward the transition region, where nuclear fusion begins to dominate the energy generation. The next phase of our journey will take us into the very heart of stellar nuclear synthesis, where the fundamental forces of nature, gravity, electromagnetism, and the nuclear forces combine to create the heavy elements that make up planet's life and ultimately ourselves. In the quiet space of our cosmic meditation, we prepare to witness the nuclear processes that power WR102's incredible luminosity and create the elements essential for the formation of planets and life. Our descent into this stellar furnace will reveal the intimate connection between stellar physics and the chemical evolution of the universe. Gently, we discover that our journey through WR102's atmosphere has already exposed us to conditions more extreme than anything found elsewhere in the solar system. Yet this has been merely the outer layer of this cosmic furnace. As we continue our descent toward the star's core, we'll encounter temperatures and densities that challenge our understanding of matter and energy under the most extreme conditions nature can produce. Like whispers in the night, the physics governing WR102's structure and evolution represent fundamental processes that have shaped the chemical composition of our galaxy. The nuclear reactions we're about to witness have been occurring in massive stars throughout cosmic time, gradually enriching the interstellar medium with the heavy elements essential for planet formation and life. As our journey continues into the nuclear-burning heart of WR102, we carry with us an appreciation for the delicate balance of forces that allows such extreme conditions to exist in a stable, long-lasting configuration. The next phase of our voyage will take us to the very center of stellar physics, where matter and energy interact in ways that forge the elements of the periodic table. Now we float toward the core of WR102, ready to witness the nuclear furnace that powers one of the most luminous stars in our galaxy. In the quiet space of stellar nuclear synthesis, we now enter the nuclear-burning core of WR102, where temperatures exceed 300 million Kelvin and pressures reach billions of times Earth's atmospheric pressure. Here, in this cosmic furnace, we witness the fundamental processes that create the heavy elements essential for planets, life, and the chemical complexity of the universe. Gently, we discover ourselves in an environment where the very nature of matter is transformed by extreme conditions. At these temperatures and densities, atomic nuclei move with such kinetic energy that they can overcome the electrical repulsion between positively charged protons and undergo nuclear fusion. The core of WR102 is actively fusing carbon and oxygen nuclei, creating heavier elements like neon, magnesium, silicon, and sulfur through a complex network of nuclear reactions. Like whispers in the night, the carbon-burning process occurring around us follows a sophisticated sequence of nuclear reactions. Carbon-12 nuclei fuse together to form neon-20, releasing an alpha particle helium for nucleus in the process. As our journey continues deeper into the stellar core, we encounter even more exotic nuclear processes. The oxygen-burning phase, which occurs at temperatures exceeding 1.5 billion Kelvin, fuses oxygen-16 nuclei together to create silicon-28, sulfur-32, and other intermediate mass elements. These reactions occur through a complex series of steps, involving the temporary formation of unstable isotopes that quickly decay. or undergo further nuclear reactions. Let's drift into understanding the role of alpha particles in these nuclear processes. Alpha particles, helium for nuclei consisting of 2 protons and 2 neutrons, are particularly important in stellar nuclear synthesis because they can be captured by existing nuclei to build up heavier elements. The alpha process is responsible for creating many of the most abundant elements in the universe, including carbon, oxygen, neon, magnesium, silicon, sulfur, argon, and calcium. Now we float toward comprehending the incredible energy density in W102's core. The nuclear fusion reactions occurring around us release approximately 10 million times more energy per unit mass than chemical reactions, like burning coal or gasoline. This enormous energy release rate is what powers the star's luminosity of 300,000 times our Sun's output, making W100 one of the most luminous objects in our galaxy. In the quiet space of quantum tunneling, we witness how nuclear fusion can occur even though the colliding nuclei don't have enough classical kinetic energy to overcome their mutual electrical repulsion. Quantum mechanics allows particles to tunnel through energy barriers that would be insurmountable in classical physics. This quantum tunneling effect is what makes stellar nuclear fusion possible at the temperatures found in stellar cores. Gently, we discover that the nuclear reaction rates depend sensitively on temperature, following a steep power law relationship. A small increase in core temperature leads to a dramatic increase in the nuclear fusion rate, which is why massive stars like W100 burn through their nuclear fuel so much more rapidly than lower mass stars. This temperature sensitivity also makes the cores of massive stars potentially unstable to thermal runaway processes. Like whispers in the night, the neutrinos produced by nuclear reactions stream through us at nearly the speed of light, carrying away a significant fraction of the energy generated by fusion, unlike photons which take hundreds of thousands of years to diffuse from the stellar core. To the surface, neutrinos interact so weakly with matter that they escape from the star, almost immediately providing a direct window into the nuclear processes occurring in the core. As our journey continues, we encounter the silicon burning process, which represents the final stage of nuclear fusion in massive stars. At temperatures exceeding 3 billion Kelvin, silicon-28 nuclei are broken apart by high-energy photons in a process called photodisintegration, then reassembled through a complex series of alpha particle captures to create iron peak elements, like chromium, manganese, iron, cobalt, and nickel. Let's drift into appreciating the neutronization processes occurring around us. As nuclear fusion proceeds to create heavier and heavier elements, the proton-to-neutron ratio in the stellar material gradually changes. Electron capture processes convert protons into neutrons, releasing neutrinos and gradually increasing the neutron content of the stellar core. This neutronization will eventually play a crucial role in the star's final collapse and explosion as a supernova. Now we float toward understanding the convective mixing that transports the products of nuclear fusion throughout W100's interior. The core of the star is convectively unstable, meaning that hot bubbles of material rise while cooler material sinks, creating a vigorous mixing process that homogenizes the composition throughout the convective region. This mixing brings the newly created heavy elements to the surface, where they can be observed in the star's spectrum. In the quiet space of stellar evolution, we witness the gradual transformation of WR102's core composition as nuclear burning proceeds. The star began its life with a core composed primarily of hydrogen, which was converted to helium during the main sequence phase. Now, in its Wolf-Rayet phase, the core consists of carbon, oxygen, and progressively heavier elements created by successive nuclear burning phases. Gently, we discover that the nuclear processes around us are not perfectly efficient. Some nuclear reactions produce unstable isotopes that undergo radioactive decay, releasing additional energy and creating daughter nuclei that may participate in further reactions. The decay of nickel-56 to cobalt-56 to iron-56, for example, powers the light curves of Type I supernovae and contributes to heating the stellar material. Like whispers in the night, the electron degeneracy pressure begins to play an increasingly important role in supporting the stellar core against gravitational collapse. As the density increases and the temperature rises, electrons are forced into higher and higher energy states, according to the Pauli exclusion principle. This quantum mechanical effect creates an additional pressure component that helps stabilize the stellar structure. As our journey continues toward the very center of WR102, we encounter conditions that approach the limits of stellar physics. The core temperature may exceed 5 billion Kelvin, and the density approaches 100 grams per cubic centimeter, conditions so extreme that they can only be sustained briefly, before leading to either explosive nuclear burning or gravitational collapse. Let's drift into contemplating the incredible precision of the nuclear physics that governs these processes. The rates of different nuclear reactions depend on fundamental constants, like the strong nuclear force coupling constant and the masses of various particles. Small changes in these constants would dramatically alter the course of stellar nuclear synthesis and the abundance patterns of elements in the universe. Now we float toward the region where iron peak elements begin to dominate the composition. Iron 56 represents the most tightly bound nucleus, meaning that fusing lighter elements into iron releases energy, while fusing iron into heavier elements requires energy input. This is why stellar nuclear synthesis naturally proceeds toward iron peak elements, but cannot continue beyond them through normal fusion processes. In the quiet space of nuclear astrophysics, we appreciate that the elements being created around us will eventually be dispersed throughout the galaxy when WR102 explodes as a supernova. The shock waves from the explosion will not only scatter these heavy elements into space, but will also trigger rapid neutron capture processes that create elements heavier than iron, including many of the rare earth elements and actinides. Gently, we discover that our journey through WR100 to S-core has taken us through the entire history of stellar nuclear synthesis. We've witnessed the alpha process that creates carbon and oxygen, the carbon-burning and oxygen-burning phases that produce intermediate mass elements, and the silicon-burning process that creates iron peak elements. This sequence represents the fundamental pathway by which massive stars create the heavy elements, essential for planetary systems and life. Like whispers in the night, the time scales for these nuclear burning phases become progressively shorter as we move to heavier elements. While hydrogen burning can sustain a massive star for millions of years, and helium burning lasts for hundreds of thousands of years, carbon burning occurs over thousands of years, oxygen burning over years, and silicon burning over days or weeks. This acceleration reflects the decreasing energy yield from fusion reactions involving heavier nuclei. As our journey continues, we prepare to witness the ultimate fate of WR102's core. The accumulation of iron peak elements creates a situation where no further energy can be extracted. From nuclear fusion, the core will continue to contract under gravity until it reaches nuclear density, at which point it will either collapse to form a neutron star or black hole, or undergo explosive nuclear burning that destroys the star. Let us drift into appreciating the profound connection between the nuclear processes we've witnessed and the existence of life in the universe. The carbon in our bodies, the oxygen we breathe, the calcium in our bones, the iron in our blood, all of these elements were forged in the nuclear furnaces of massive stars. Like WR102, we are literally made of stardust, connected to the cosmos through the nuclear processes that occur in stellar cores. Now we float toward the climactic moment of our theoretical journey. As WR102's core approaches the conditions that will trigger its final transformation, the next phase of our exploration will examine how the extreme physics we've encountered leads inevitably toward the star's explosive end, and its contribution to the chemical evolution of the galaxy. In the quiet space of cosmic perspective, we recognize that our journey through WR100 to S nuclear furnace has revealed the fundamental processes that drive stellar evolution and chemical enrichment throughout the universe. The extreme conditions we've experienced represent nature's most powerful alchemical laboratory, where the basic building blocks of complexity are forged from the simplest elements. Through the fundamental forces of physics, gently, we discover that the nuclear reactions we've witnessed are not just local phenomena occurring within WR102, but representative of processes that have been occurring in massive stars throughout cosmic history. These reactions have gradually enriched the interstellar medium with heavy elements, making possible the formation of rocky planets and the complex chemistry essential for life. Like whispers in the night, the physics of stellar nuclear synthesis reveals the deep connections between quantum mechanics, nuclear physics, thermodynamics, and gravity. The extreme conditions in WR102's core represent a natural laboratory, where these fundamental forces combine to create the elements that make up our world and our bodies. As our journey continues toward its culmination, we carry with us an appreciation for the remarkable processes that have transformed us from mere observers into participants in the cosmic cycle of stellar death and rebirth. Our theoretical passage through WR102 has revealed not destruction, but creation, the ongoing process by which the universe builds complexity from simplicity. Through the patient work of stellar nuclear synthesis, now we float toward the final phase of our cosmic meditation, ready to explore how the extreme physics of WR102 contributes to the grand narrative of cosmic evolution. In the quiet space of our cosmic contemplation, we now step back from the intense nuclear furnace of WR102's core to consider the broader significance of our theoretical journey. Like whispers in the night, the extreme physics we've encountered in this stellar giant connects us to fundamental processes that have shaped the universe for billions of years, creating the elements essential for planet's life and the rich complexity we observe throughout the cosmos. Gently, we discover that Wolf-Rayet stars like WR100 play a crucial role in what astronomers call galactic chemical evolution, the gradual enrichment of the interstellar medium with heavy elements. Over cosmic time, when our galaxy first formed, it contained only hydrogen and helium, the light elements created during Big Bang nuclear synthesis. Every element heavier than lithium in the periodic table has been forged in the nuclear furnaces of stars and dispersed through stellar winds and supernova explosions. As our journey continues through this cosmic perspective, we appreciate that WR102 is not just consuming nuclear fuel and generating energy, but actively creating and dispersing the building blocks of future generations of stars and planets. The powerful stellar winds we encountered during our approach are carrying carbon, oxygen, neon, magnesium, and other heavy elements into the surrounding interstellar medium at rates of approximately 1 solar mass per 100,000 years. Let's drift into understanding the life cycle of heavy elements in our galaxy. The carbon, oxygen, and other elements being created in WR100's core and dispersed through its stellar winds will eventually become incorporated into giant molecular clouds, the stellar nurseries where new stars and planetary systems form. Some of these elements will end up in the atmospheres of new stars, while others will condense into solid grains that can aggregate to form asteroids, comets, and planets. Now we float toward contemplating the supernova explosion that awaits WR102 in the cosmically near future. When this massive star can no longer sustain nuclear fusion in its core, it will undergo catastrophic gravitational collapse, followed by a tremendous explosion that will outshine an entire galaxy for several weeks. This supernova will not only disperse the heavy elements created during WR102's lifetime, but will also trigger rapid nuclear processes that create elements heavier than iron. In the quiet space of nuclear cosmochrony, we can trace the history of element formation in our galaxy through the abundance patterns observed in different stellar populations. The oldest stars, formed when the galaxy was young, contain only tiny amounts of heavy elements, reflecting the fact that few generations of massive stars had lived and died by that time. Progressively younger stars show higher abundances of heavy elements, documenting the ongoing process of galactic chemical enrichment. Gently, we discover that the oxygen we breathe, the carbon in our bodies, and the silicon in the rocks beneath our feet all have their origins in stars like WR102. Oxygen is created primarily through helium burning in massive stars, carbon through the triple alpha process, and silicon through oxygen burning. The iron in our blood comes from the silicon burning processes occurring in the final moments before stellar core collapse. while elements heavier than iron are created during supernova explosions through rapid neutron capture. Like whispers in the night, the shock waves from supernovae like the one that will eventually mark WR102's death propagate through the interstellar medium, compressing gas clouds and triggering the formation of new stars. This creates a feedback mechanism where stellar death leads to stellar birth, ensuring that the process of star formation continues over billions of years. Our own sun and solar system may have formed in such a compressed region, triggered by the explosion of an ancient massive star. As our journey continues, we consider the remarkable fact that the nuclear processes we witnessed in WR102's core are among the most efficient energy sources in the universe. Nuclear fusion converts approximately 0.7% of the rest mass of hydrogen into energy according to Einstein's famous equation E equals mc. This efficiency is far greater than chemical reactions which convert about K-9 of the rest mass, but still much less than the 100% conversion possible through matter-antimatter annihilation. Let us drift into appreciating the role of massive stars like WR102 in regulating star formation throughout the galaxy. The intense radiation from these luminous giants can ionize vast regions of space, creating H2 regions that prevent nearby gas clouds from collapsing to form new stars. The stellar winds and eventual supernova explosions can also blow away the gas supply needed for star formation, creating bubbles and cavities in the interstellar medium. Now we float toward understanding the connection between WR102 and the formation of compact objects, neutron stars and black holes. When this massive star undergoes core collapse, the extreme density reached during the collapse may be sufficient to overcome electron degeneracy, pressure and crush protons and electrons together to form neutrons. If the core mass exceeds about 2 to 3 solar masses, even neutron degeneracy pressure cannot halt the collapse, and a black hole will form. In the quiet space of gravitational wave astronomy, we recognize that the eventual fate of WR100 may contribute to our understanding of the most extreme physics in the universe. If WR102 is part of a binary system and leaves behind a compact remnant, it could eventually merge with its companion in a process that generates gravitational waves, ripples in space-time itself, that can be detected by instruments like LIGO and Virgo. Gently, we discover that studying Wolf-Rayet stars like WR100 provides crucial insights into stellar evolution models and the initial mass function of stars. These observations help astronomers understand how the most massive stars form, evolve, and die, which in turn affects our models of galactic chemical evolution, supernova rates, and the formation of compact objects throughout the universe. Like whispers in the night, the extreme conditions we encountered during our theoretical fall into WR100 represent natural laboratories for testing fundamental physics under conditions that cannot be reproduced on Earth. The temperatures, densities, magnetic fields, and radiation environments found in and around massive stars push our understanding of thermodynamics, plasma physics, quantum mechanics, and general relativity to their limits. As our journey continues, we reflect on the interconnectedness of cosmic phenomena revealed by our exploration of WR102. The nuclear processes powering this star are intimately connected to the formation of planetary systems, the chemical composition of Earth's atmosphere and oceans, and even the biochemical processes that make life possible. We are not separate from the cosmos, but part of an ongoing story of stellar death and rebirth that has been unfolding for billions of years. Let us drift into contemplating the future evolution of our galaxy, as revealed by our study of massive stars like WR102. Over the next several billion years, the most massive stars will continue to enrich the interstellar medium with heavy elements, gradually increasing the metallicity of new stellar generations. This chemical evolution will affect the formation and characteristics of planetary systems, potentially making Earth-like worlds more common as time progresses. Now we float toward appreciating the role of WR102 and similar stars in creating the conditions necessary for complexity and life in the universe. The carbon-based chemistry that underlies all known life requires the presence of heavy elements that can only be created in stellar cores. The energy sources that power planetary atmospheres and drive geological processes also depend on the presence of radioactive elements created in massive stars. In the quiet space of astrobiology, we recognize that our theoretical journey through WO102 has revealed the cosmic context for life itself. The extreme physics we encountered, from stellar winds and radiation pressure to nuclear fusion and element creation, represents the universe's way of building complexity. From simplicity creating the conditions necessary for the emergence of stars, planets, and ultimately life. Gently, we discover that the time scales involved in these cosmic processes span an enormous range, from the microseconds required for nuclear reactions to the billions of years needed for galactic chemical evolution. Our theoretical passage through WO102, which might last only minutes in reality due to the extreme conditions, connects us to processes that have been occurring throughout cosmic history. Like whispers in the night, the story of WO102 reminds us that the universe is not a static collection of objects, but a dynamic, evolving system where matter and energy are constantly being transformed and recycled. Stars are born from the ashes of previous generations, planets form from the debris of stellar explosions, and life emerges from the chemical complexity made possible by billions of years of stellar nuclear synthesis. As our journey continues toward its peaceful conclusion, we carry with us a deep appreciation for the role of extreme astrophysical environments in shaping the universe we inhabit. The hostile conditions we encountered in WO102, temperatures of hundreds of thousands of degrees, pressures billions of times greater than Earth's atmosphere, radiation fields intense enough to ionize any atom, are not barriers to cosmic evolution but essential engines of creation. Let us drift into recognizing that our theoretical fall into WO102 has been a journey not toward destruction but toward understanding our cosmic heritage. Every atom in our bodies, except for hydrogen, was forged in the nuclear furnace of a massive star similar to WO102. We are made of stardust in the most literal sense, connected to the cosmos through the nuclear processes that occur in stellar cores throughout the universe. Now we float toward the realization that extreme astrophysical environments, like those found in WO102, are laboratories, where the fundamental laws of physics are tested under conditions far beyond what we can achieve on Earth. The quantum mechanics, thermodynamics, nuclear physics, and general relativity that govern these environments represent our best understanding of how the universe works at the most fundamental level. In the quiet space of cosmic meditation, we appreciate that the journey we've taken through WO102's stellar wind, atmosphere, and nuclear burning core has revealed the intimate connections between physics, chemistry, astronomy, and biology. The same nuclear processes that power this massive star are responsible for creating the elements essential for rocky planets and carbon-based life. Gently, we discover that the study of extreme stellar environments like WO102 continues to reveal new physics and challenge our understanding of how matter and energy behave under the most extreme conditions. Future observations with advanced telescopes and instruments will undoubtedly reveal new insights into the physics of massive stars and their role in cosmic evolution. Like whispers in the night, the legacy of WO102 will continue long after this particular star has exploded as a supernova and dispersed its heavy elements into the interstellar medium. The elements created in its nuclear furnace will become incorporated into future generations of stars and planets, continuing the cosmic cycle of stellar death and rebirth that has been shaping our galaxy for billions of years. As our journey continues toward its gentle conclusion, we recognize that our theoretical exploration of WO102 has been more than just a study of extreme stellar physics. It has been a meditation on our place in the cosmic order and our connection to the fundamental processes that shape the universe. The nuclear reactions we witnessed, the element creation we observed, and the extreme conditions we encountered all contribute to the ongoing story of cosmic evolution. Now we float toward a peaceful understanding that the apparent hostility of environments, like WO102's interior, masks a deeper truth about the universe's creative processes. The extreme conditions that would instantly vaporize any material object are the same conditions that forge the elements essential for complexity, life, and consciousness. In the cosmic perspective, destruction and creation are different aspects of the same fundamental processes. In the quiet space of our final reflections, we appreciate that the knowledge gained from studying massive stars like WR100 contributes to our understanding of stellar evolution, galactic chemical evolution, supernova explosions, and the formation of compact objects. This knowledge, in turn, informs our models of planetary system formation, astrobiology, and the search for life elsewhere in the universe. Gently, we discover that our journey through WR102 has revealed the profound interconnectedness of all cosmic phenomena. The nuclear processes occurring in this distant star are intimately connected to the formation of our solar system, the composition of our planet, and the biochemical processes that sustain life on Earth. We are not observers of the universe but participants in its ongoing evolution. Good night from the sleepy scientist.